Hello students, we are going to have a look at the JEE Advanced 2025 questions. This is paper 1. So let's go through the questions. The first question given is from inorganic chemistry, the heating of ammonium nitrite and ammonium nitrate at the respective temperature gives the nitrogen containing compounds X and Y. Identify X and Y. Okay, ammonium nitrite. Ammonium nitrite, if heated, its thermal decomposition will be giving us N2 gas along with H2O, and ammonium nitrate, if heated, it will be giving a special compound N2O along with H2O. Generally, ammonium salts containing oxidizing anions other than nitrate is going to give us dinitrogen on thermal decomposition. So here our answer is option A. The correct order of wavelength maxima of absorption band in the UV visible region for the given complexes is, we know as the ligand strength increases, all being octahedral complexes, we can say delta O, the splitting energy increases, and therefore frequency of absorption or energy of absorption increases, and hence wavelength of light absorbed decreases. So stronger the ligand, lowest is the wavelength absorbed. So cyano is the strongest ligand, and ammonia along with aqua ligand, ammonia along with chloride ligand. So this is the order of ligand strength, and therefore correct answer here. Okay, so we want the opposite order of ligand strength. So wavelength absorbed follows the reverse order if we compare ligand strength. So option A is the correct answer here, and this was taken directly from your NCERT book. Here you have to remember that all metals are same. Okay, CO3 plus cobalt 3 plus is the central atom in all the cases. Therefore its ligand strength is the only factor that determine the wavelength of absorption. One of the products formed from the reaction of permanganate ion with iodide ion in neutral aqueous medium is, you know from D&F block chemistry that permanganate ion in acidic medium oxidizes iodide ion to iodine, and in neutral or faintly alkaline medium iodate is the product. So in neutral aqueous medium or in faintly alkaline medium, option B is the correct answer, and if it's acidic medium, option A is the correct answer. So here answer is option B. Consider the depicted hydrogen in the hydrocarbons given below. The most acidic hydrogen is. Okay, so acidity of hydrocarbons or organic compounds in general, if we compare it, we will go by comparison of stability of conjugate bases, which are anions. Okay, we will generate anion from all these and compare their stability. So from here we will get such a resonance stabilized anion, and in next case we will be getting that particular anion. From third, conjugate base generated will be this one, and from fourth, the conjugate base is going to be that one. We can find resonance everywhere in the anions, but in second case, okay, in second anion, the resonance leads to aromaticity. Because of this resonance, the ring is going to have 6 pi electrons in it. Okay, so take one of its resonance structures and verify that. So this is another resonance structure for that conjugate base. So that confirms aromatic nature of the ring. So option B is containing the most acidic hydrogen, which is explained on the basis of extra stability of the conjugate base, the aromaticity of the conjugate base anion. So this is a one or more than one correct type section. Regarding the molecular orbital energy levels for homonuclear diatomic molecules, the incorrect statements. Okay, incorrect statements we need to identify. Bond order of Ne2 is 0. That is a true statement. Be2 or Ne2 or He2, these are having 0 bond order. The highest occupied molecular orbital of F2 is sigma type. Fluorine molecule is having pi star 4 in its highest energy level. Okay, and the sigma star is vacant. So it is wrong that HOMO is sigma type. HOMO is pi type. Or else we can say LUMO is sigma type. This is lowest unoccupied molecular orbital. LUMO is sigma type. But HOMO, highest occupied molecular orbital, is pi type. So B is an answer because it's a wrong statement. Bond energy of O2 plus is smaller than bond energy of O2. Bond energy of O2 and O2 plus, if we compare, we can take bond order as a reference. Bond order of O2 is 2 and bond order of O2 plus will be 2.5 from its MO theory. So bond energy of O2 plus will be definitely higher than bond energy of O2. So smaller is a wrong phrase. So this is an answer. Bond length of Li2 is larger than bond length of B2 is correct because we know size of atoms varies, like lithium is larger than boron. From left to right in a period, atomic size decreases. So Li2 is expected to be larger than B2. Yes, in terms of bond length also. So B and C are the answers here. The pairs of diamagnetic ions are, so if you look at the options, the option is talking about 4 different elements. So it's mentioning about lanthanum, then cerium, ytterbium and lutetium. So we know the periodic table very well and the electronic configuration of every element. Lanthanum, all of these 4 are members of 6 period. So 6 is 2, 5d1, 4 of 0 is the configuration of lanthanum because this is the 3rd element of 6th period and this is the 4th element of 6th period. So 6 is 2, 5d1, 4 of 1 is the configuration of cerium. Both are having exceptional electronic configuration. Then ytterbium, 6s2, 5d0, 4 of 14 is the configuration, and lutetium, 6s2, 5d1, 4 of 14 is the configuration. So we know the element configurations. Now if you take a tripositive ion of lanthanum, all these 3 electrons will be removed and no unpaired electrons will be left. So lanthanum 3 plus is going to be diamagnetic, and similarly C4 plus also. You know, this is the fourth element of 6th period and we are removing all those 4 valence electrons. So none of the electrons will be unpaired then. So it's also going to be diamagnetic. And if you go to ytterbium and lutetium, ytterbium 2 plus, 6s2 will be removed and we will be having then 4 of 14 in the valence. So 4 of 14 is a paired configuration, so it's diamagnetic. And lutetium 3 plus, also will be having 4 of 14 configuration because these 3 electrons are getting removed. So these are also having diamagnetic nature, and therefore we can say lanthanum 2 plus, cerium 3 plus, ytterbium 3 plus, lutetium 2 plus, these are going to be paramagnetic. So A and B are the answer here. For the reaction sequence given below, the correct statements are, okay, addition reaction, electrophilic addition gives haloalkane, and Finkelstein reaction is a preparation of iodoalkane by halogen exchange, and Schwartz reaction will be giving corresponding fluoroalkane also. So we identified P, Q and R. Now we want to identify the correct statements about P, Q and R. CX bond length in P, Q and R follows the order Q highest, correct. Q is having the highest bond length because it is containing iodine atom. Then R second highest, that is going to be wrong. P is going to be second highest and R is going to be smallest in terms of CX bond length because fluorine is smallest atom. So the correct order must be QPR, not QRP. So it's not an answer. CX bond enthalpy in PQ and R follows the order RPQ. Let's check. Bond enthalpy will be highest for CF bond. So R is correct. Now second highest for P, that is bromine case, that is true, and third for iodoalkane. Okay, so as the size of halogen increases, bond becomes weaker and weaker. So bond enthalpy decreases as the size increases. So this is a true statement. Relative reactivity towards SN2 reactions follows the order PRQ. P is not the one which is most reactive in SN2 or SN1. Iodoalkane will be most reactive. And least reactive will be R. Okay, least reactive will be R, which contains fluorine in it. So this is an incorrect arrangement of species. Relative reactivity should follow the order Q, then P, and finally R. Now pK values of the conjugate acids of leaving groups in PQ and R. Leaving groups, these are famous for substitution reactions. Haloalkanes, their favorite reaction is nucleophilic substitution reaction because in general halogens are good leaving groups. So we are talking about conjugate acids of halide ions here. Conjugate acid of leaving group in P is HBr. Conjugate acid of leaving group in Q is HI, and conjugate acid of leaving group in R is HF, although F is not a good leaving group. Okay, but considering it's a general case, F is the leaving group in R. Okay, now we have no other option. So if you compare acidity of these three, from P block that HI is most acidic, therefore more negative is the pK value, and this is going to be an incorrect option because Q has to be the one with the lowest pK value, most negative pK value, then HBr, and highest pKa goes for HF because that is the weakest acid. So this is the weakest acid, this is the strongest acid, which you know from P block also. So D is a wrong statement. So only B is correct here. Now we have a numerical section where we have to enter our answer correct up to 2 decimal places. In an electrochemical cell, dichromate ions in aqueous acidic medium are reduced to Cr3+. Okay, so the reaction involved is, the half reaction involved is Cr2O7 2- becoming chromium 3+. We need to find out the current that flows through the cell for this many time to produce 1 mole of chromium 3+. If we want to form 2 moles of chromium 3+, we have to pass 6 farad of electricity. Okay, if you look at the oxidation number changes, this is from +12 for 2 chromiums, chromiums 2 + 6. So there has to be passage of 6 farad of electricity in order to generate 2 moles of chromium 3+ at the cathode. Now, therefore, for 1 mole of chromium 3+, we should be passing 3 farad of electricity. So, for 1 mole chromium 3+ requires 3 farads, which is 3 into 96500 coulombs electricity, right? So we need to find out I. We know Q is I times T, and Q in coulombs, we know 3 into 96500, and I is the unknown, and time in seconds we have to enter because amperes is coulomb per second. So 48.25 minutes multiply 60, that is the okay. So we will get I value is 100 coulomb per second. So 100 is the answer in amperes. At 25 degrees Celsius, the concentration of H plus ions in 10 raised to minus 3 molar aqueous solution of a weak monobasic acid having Ka value 4 into 10 raised to minus 11 is X into 10 raised to minus 7 molar. The value of X is. Okay, so here we need to consider the H plus concentration from water as well. Okay, because if you simply calculate, contribution from Hx only using our normal logics, concentration of Hx initial was C and finally it is C minus some X. So X, and being a weak acid, as evident from the K value, we can neglect X and this is nearly equal to C only. So X into X divided by C is going to be Ka, and X is nothing but H plus concentration, right? So H plus concentration square is C times Ka into C. So 4 into 10 raised to minus 11 times C was 10 raised to minus 3, which is 4 into 10 raised to minus 14. So H plus concentration is going to be 2 into 10 raised to minus 7 molar. You know, this is very close to, this is very close to normal H plus concentration in simple water medium, okay, pure water. So we need to consider the H plus contribution from solvent also. For that they have clearly given the Kw value as well. Okay, so at 25 degrees Celsius, Kw of water is 10 raised to minus 14. So consider its contribution also. Okay, so here we need to take H plus contributed by Hx as well as H plus concentration contributed by H2O dissociation. So let's do it once again. Hx dissociating to form H plus and X minus. Initially it was C concentration and 0 was the initial concentration of H plus, and C minus C alpha, C alpha, these are the equilibrium concentration. But at same time H2O is also dissociated in an equilibrium. Okay, so these are aqueous species. H2O is liquid, let's consider it pure, and those are aqueous species. These are the two simultaneous equilibrium going on in the medium, and at equilibrium, from this dissociation, if we are going to generate X amount of H plus, definitely we will be getting X amount of OH minus in the medium. We will not be writing anything here because it is assumed pure. Okay, so this is the equilibrium concentrations, and here it is the case like both equilibriums are going in one vessel itself. So we can find a common species involved in the two equilibria, that is H plus. So actual concentration of H plus is not C alpha, not X, it is C alpha plus X. C alpha obtained from Hx dissociation and X obtained from H2O dissociation. So in the equilibrium row we have to rewrite H plus concentration by same value, and that is C alpha plus X logically. Okay, ionic equilibrium, we have to logically take certain values, and here this is the logic. Both are, if we assume both acidic, Hx is acid and H2O, let's assume this is a weak acid. Okay, it's a weak acid as well as weak base, right, because it donates H plus as well as OH minus, therefore it's amphoteric. So both are weak electrolytes, let's consider that way. Then H plus obtained from this dissociation plus H plus obtained from that dissociation, that is the effective concentration of H plus and logical value for that in this case. Now let's apply law of chemical equilibrium in both cases. It has to be true that C alpha plus X into C alpha divided by C minus C alpha, which is close to C, is equal to Ka of Hx, and there C alpha plus X times X is equal to Kw of water at this temperature. These are the two equations, and if we rearrange it, now this is a simple mathematical trick only. to solve this expression. Ka into C is the value for this, and C alpha plus X into X is Kw. Now what we need to find is H plus concentration in this medium, and H plus concentration in this medium is nothing but C alpha plus X. So we need to get the value of C alpha plus X part. So, and both these equations has to be true here. Both these equations are happening, are varied in this case because these are two simultaneous equilibria happening in the medium. So how to solve these two equations? Just add them. Okay, just add them. If we add these two equations, let's call this equation 1 and that equation 2. Now do 1 plus 2. That's just a mathematical trick. If we do 1 plus 2, we will get C alpha plus X, which is common for both LHS. And in addition, from this equation we have C alpha, and from that we have X. So C alpha plus X, and is equal to on RHS KAC plus KW. Okay, and this is H plus square only. So this is H plus into H plus, which is H plus square. So H plus is going to be square root of KAC plus KW, and we know the value of KAC and KW. Ka is 4 into 10 raised to minus 11, and concentration of H plus initial one was 10 raised to minus 3, plus Kw is given as 10 raised to minus 14. Right, so H plus concentration is going to be root of 5 into 10 raised to minus 14, which is square root of 5 into 10 raised to minus 7 molar. And you know, square root of 5 is approximately 2.236. Okay, and the final answer key, the range that IITK has given for this question is 2.2 to 2.3. So if you have entered any value ranging from 2.2 to 2.3, you will get full marks for this question. So our answer is actually root of 5, square root of 5. Okay, square root of 5. Molar volume of a van der Waals gas can be calculated by expressing van der Waals equation as a cubic equation with Vm as the variable. Ratio of coefficients of Vm square to the coefficient of Vm for this gas with A value and B value as given here at 300 Kelvin T and 300 atm pressure is dash. Okay. So here we know van der Waals equation is P plus An square by V square times V minus Nb equals nRT. And this question restricts the substance to 1 mole. So we can rewrite the equation like P plus A by Vm square, where Vm is the volume of 1 mole. Okay. So Vm is nothing but V by N, total volume of the gas divided by number of moles. So V by N is replaced by Vm, and Vm minus B equal to RT. Now we need to generate a cubic equation in the variable Vm. So let's cross multiply it. P Vm square plus A into Vm minus B is equal to, bring Vm square on RHS, Vm square RT. Again expand this, P Vm cube minus P Vm square B plus AVM minus AB is equal to Vm square RT. So you can see two terms having Vm square as a variable. So bring them together. So the final equation will be PVm cube minus PB plus RT Vm square plus AVM minus AB equal to 0. So this is the required cubic equation. Now we want the ratio of coefficients of Vm square to that of Vm. Coefficient of Vm square is minus PB plus RT, and coefficient of Vm is constant A. So our final answer is going to be the value of this expression. Clearly the value is given for every time here. P is given as 300 atm. B value is given as 0.06 decimeter cube per mole plus R value is given as 0.082 dm cube atm per mole per Kelvin, and temperature is given as 300 K. So this divided by A value is 6 dm raised to 6 atm mole raised to -2. Okay. So you can see everywhere you have decimeter cubes, everywhere you have atm, everywhere you have mole and Kelvin only. So this equation is dimensionally okay, and you just get the numerical value of this expression, and that will be the final answer. The exact value goes like -7.1, and IITK has given full marks if somebody has written answer in the range -7 to -7.2. Okay. Considering ideal gas behavior, the expansion work done in kilojoules when 144 grams of water is electrolyzed completely under constant pressure is at 300 Kelvin is. So 144 gram is 8 moles of H2O. Let's write the balanced chemical equation for electrolysis of water. Yes, H2O dissociates to H2 plus half O2. So it's a balanced equation for electrolysis of H2O. Now, from the equation it is clear that 1 mole of liquid decomposes to 1.5 moles of gases. 1 mole H2O, which is in liquid state, is giving out total of 1 plus half, that is 1.5 mole of ideal gas. Let's assume ideal behavior. And here we have taken 8 moles of H2O for electrolysis. Therefore, we will be getting total of 12 moles of gases at the end of the process. So, there is definitely an expansion occurring because initially we don't have any gas and we have to keep same pressure from beginning to end. So, with the generation of gas, there is expansion occurring, and delta Ng for this process, okay, expansion or the expansion is valid for gaseous substances only. We neglect it for liquids and solids. So, we are focusing on delta Ng for the process. Delta Ng for the process is 12. Initially we don't have any gases, and finally we have 12 moles of gases. So 12 mole is the delta Ng, change in number of moles of gas in this process. So it's called expansion. Now what we want to find out is the pressure, the work done in this process. We know any work done dW in expansion conditions is going to be minus P external times dV of the process, and here minus P external dV we can substitute using ideal gas equation like, you know, V is nRT by P, nRT by P for ideal gas, and in this case number of moles of gas is varying in the process. Okay, generally in our expansion process number of moles of gas is not altered. We are taking a fixed amount of gas and just varying its pressure and volume. Here something else happens. Okay, this is a part of reaction. So pressure is kept constant and volume is changing due to number of moles variation. So dV we can rewrite like dN RT by P, where RT and P are constants, they are not varying, and we can assume external pressure and internal pressure of the gas same. Either you can put here P gas and there P gas, or you can put here P external, there P external. Okay, in the second row, because both are equal. Okay, gas pressure is equal to external opposing pressure. But in first equation, we cannot simply alter this, but because this is definition of work done. Definition of work done. Okay, so dW is always minus P external dV, and in certain special cases, it is going to be minus P gas dV. Okay, that is same pressure condition cases. The reversible case. Okay, all right. So here, P external cancel out, and total work done will be integral minus dN RT. RT is a constant, so minus delta Ng, okay, RT is the work done for this process. We know delta Ng, we know R, we know T. So minus 12 mole times R is 8.3 joules per Kelvin per mole times T is 300 K. So on solving this expression, we will be getting minus 298880 joules as the work done, and in kilojoules it is minus 29.88 kJ. So that is our answer. And IITK has given full marks if somebody has written answer in the range 29.8 to 29.95 or minus 29.95 to minus 29.8. These are all accepted values as per IITK. You know why there is some flexibility with the sign of the work done? That's just because of, okay, I guess that's just because of the expansion work mentioning in the question phrase. If it was simply the work done when this much electrolysis is occurring, then you should be giving the negative sign. Okay, since they are specifically saying expansion work, we know expansion work is generally negative. Okay, expansion work is negative because system is doing work. So due to that phrasing, they will accept the answer if you are not including negative sign also. Okay, otherwise if it was simply what is work done in this process, you should be writing minus 29.88. okay, that is a perfect answer. This will not be accepted in that case, but here both were accepted. The monomer X involved in the synthesis of nylon 66 gives positive carbylamine test. Okay, so this is from polymers chapter, and you know nylon 66 is prepared from two monomers. It's a condensation polymer. One is hexamethylene diamine and the other is adipic acid. These are the two monomers. Both are having 6 carbon atoms in it. Therefore the name. So the monomer X here should be hexamethylene diamine because it gives positive carbylamine test. Positive carbylamine test will be given by primary amino group containing compounds. Okay. So X is hexamethylene diamine, and 10 moles of X are analyzed using Dumas method. Okay, you know in Dumas method we are heating the amine with copper oxide oxidizing agent in a combustion train, and all the nitrogen is converted to En2 gas, and all the C is going to CO2 and hydrogen is going to H2O. So that is basically combustion process where carbon, hydrogen and oxygens are converted to suitable targets. Alright, so here En2, 1 mole of N2 is obtained from 1 mole of hexamethylene diamine, because one molecule of hexamethylene diamine as well as nitrogen gas, both are having same number of nitrogen atoms. Okay, so 1 mole is giving 1 mole of N2. Here they have taken 10 moles of hexamethylene diamine, so 10 moles of N2 will be produced. 10 moles of N2 will be obtained from 10 moles of hexamethylene diamine, and its mass is going to be 280. Okay, molar mass of N2 will be 28 grams per mole. So 10 mole 280 is the correct answer. The reaction sequence given below is carried out with 16 moles of hex. The yield of major product in each step is given below the product in parenthesis. We need to find out the final amount in grams of S. Okay, so let's find the structure of P, Q, R, T and S first, then go with calculation. So first thing that happens is a Fittig reaction and followed by hydrolysis of acetal, giving back a carbonyl product. Okay, so you know this is a masked benzaldehyde, ethylene glycol, acetal it is. So first with sodium triether, we get a coupled product. That's Fittig reaction. And with H3O plus, the acetal hydrolyzes to aldehydic unit here with the release of ethylene glycol. So that is the structure of P. Okay, let's write the structure of P there itself. Now let's continue with the reaction. Now this is treated with NaOH under hot conditions. So OH minus heat will give Cannizzaro reaction intramolecular here. Hydride will be transferred from one aldehyde to the other aldehyde. So this becomes carboxyl then, and that becomes alcohol. So followed by acidification will give us the COOH unit in it. So first CO minus and CS2OH are produced, and on acidification CO minus becomes COOH, fully protonated. So that is just an intramolecular Cannizzaro reaction. Okay, so that is the structure of Q. Next thing that happen is soda lime decarboxylation. Soda lime decarboxylation of the carboxylic acid unit. So this carboxyl group is removed and replaced with hydrogen. So structure of R is going to be that one. So now onwards it is going to carry only single oxygen atom. The rest of the elements are carbon and hydrogen only. So there is a preparation of hydrocarbon, soda lime decarboxylation. So you got this structure which is called as R here, and followed by PBr3 reaction. PBr3 is a reagent for nucleophilic substitution of alcohol where haloalkanes are generated. So benzyl alcohol becomes benzyl halide, and this is a structure of T. Then this is treated with R again. R is this one in presence of NaH, which is a strong base. You know, when alcohol is taken with Na in presence of a strong base, it is forming the alkoxide, which shows the acidic property of alcoholic unit. Okay, this is the structure obtained from the reagent combination R with NaH. It's not NaOH, it is NaH. Okay. So these two are getting reacted. Okay, this is reacting with that, and that is simply Williamson ether synthesis, because this is an alkoxide, that is a primary alkyl halide. Williamson ether synthesis will occur, and this is nothing but an ether. So this does an SN2 reaction over there, which is called as Williamson synthesis, and ether is the product. So final structure is that one. This is structure of S, which is an ether, and its molar mass is 350 grams per mole. Now let's look at the yields given for each of these steps. First compound is obtained in 100% yield. If it is 100% yield, you know, from 16 moles of X we will be maximum getting 8 moles of coupled product. This we started with 16 moles of X, and you know 2 X is clubbed together to form P. So full yield is 8 moles of this biaryl compound. Wood's reaction, fatigue reaction, these are all behaving similarly. Okay, full yield is half mole from 1 mole. Now from here to there, all are like 1-to-1 conversion. So 8 mole maximum will give 8 mole, and 50% yield is actually 4 mole here. So actual yield is 4 mole only. Again 4 mole can maximum give 4 moles of that, but 50% of that only obtained. So 2 moles of this is actually obtained. Again 2 moles of this can maximum give 2 moles of that haloalkane, but only 50% of that is obtained, which is 1 mole of haloalkane. Again same, 1 mole of this can get converted to 1 mole of ether maximum, but only half of that is produced here, which is 0.5 mole. 50% is the yield. So half mole of ether is generated, half mole of S is generated. So the mass of S generated will be 175 grams. Right. So in the first step, if you have some confusion about the structure of P, first of all we can imagine that this is Wood's fatigue reaction, but for confirmation the molar mass of the compound is given. You can verify with the structure. Okay. Next we have matrix match type section. We need to identify the correct matching from the options. Okay, so this is a simple question from salt analysis regarding categorization and precipitation reagent for each group. Okay, so let's identify the group names, then we will be easily getting the correct matches. Copper 2 plus is group 2, aluminum 3 plus is in group 3, manganese 2 plus is in group 4, barium 2 plus is in group 5, and magnesium is in group 6. Now the reagents in list 1, passing H2S in presence of NH4OH. This is a reagent for group 4, alkaline sulfides. Now acidic sulfides is group 2. Ammonium carbonate in presence of ammonia is group 5 reagent, and ammonium hydroxide in presence of ammonium salt, that is going to be third group reagent. So 4 matches with this. This is going to 4, that is matching with 2, and this is matching with 1. So 3, 4, 2, 1 is the correct combination. 3, 4, 2, 1. Option A is going to be correct. Next one is again from organic chemistry. In list 1, certain name reactions have been mentioned, and in list 2, there are certain reaction sequences given, and we need to identify, yes, the reaction which gives the starting material for the name reaction. Okay, that means we need to identify, for Stephan reaction, we need to identify the reaction which gives a nitrile, because Stephan reaction is the conversion of nitrile to aldehyde. Sandmeyer reaction, it's a conversion of aryl diazonium salts to haloarine, let's say, and therefore we need to identify the reaction which gives aryl diazonium salts, arene diazonium salt. Okay, so that's the idea. First reaction is very familiar, Ittard reaction, and benzaldehyde is the product. Benzaldehyde is the product. And benzaldehyde, yes, benzaldehyde is a suitable option for, yes, Cannizzaro reaction. Is benzaldehyde can show Cannizzaro reaction because it's a aldehyde without any alpha hydrogen. So it may match with 1. S may match with 1. Benzoic acid with PCl5, benzoyl chloride will be generated. Benzoyl chloride with ammonia, very easy nucleophilic acyl substitution will happen. Amide will form. Acid chloride reacts with ammonia to form amide, and amide with P2O5 in heated condition will give nitrile, that's the dehydration of amides. Okay, so amide to nitrile conversion occurred in the last step. So cyanobenzene is obtained. Cyanobenzene is a suitable starting material for Stephan reaction. Now nitrobenzene with FeHCl, aniline is produced. Aniline with HCl and NaNO2 at low temperature will get benzene diazonium chloride. So benzene diazonium chloride is the starting material for Sandmeyer reaction. Toluene with chlorine H2O. Toluene with chlorine H nu and followed by hydrolysis. As per NCERT representation, benzaldehyde is the expected product, although there are multiple possibilities. Okay, it could be benzyl alcohol, it could be benzaldehyde, or it could be benzoic acid as well, depending on the amount of equivalence of chlorine got reacted with toluene. But our general assumption is, as per NCERT representation, this reaction is going to give a benzaldehyde as the product, because this is a standard preparation of benzaldehyde by partial side chain oxidation. Okay, so Tollens reagent again confirms that in first step we are getting benzaldehyde, because Tollens reagent is a reagent for oxidation of aldehyde to carboxylic acids. Now SOCl2 will give acid chloride, and acid chloride with ammonia will produce amide as the product. Okay, so amide is a good, it's a starting point for Hofmann bromide degradation. Yes, so we got all the matches. Now let's identify the product in last case also. Aniline, acetic anhydride, acetanilide is obtained. NHAC. NHAC nitration will give para nitro product as the major product, and aqueous NaOH will give hydrolysis of this amide portion to form amine. Okay, so para nitro aniline is the product of reaction sequence 5, which is not a characteristic starting material for any of the reactions mentioned here. So this has to be the correct matching. 2, 3, 4, 1. 2, 3, 4, 1 is the correct sequence. List 1 is showing certain compounds, and observations are given in list 2. Okay. So reaction with phenyl diazonium salt gives an yellow dye. Yellow dye is formed with aniline. Aniline yellow, you know, right? So para aminoazobenzene is formed. That's aniline. That is the yellow dye. So aniline will be matching with 1. Aniline is able to form a yellow dye with phenyl diazonium salt. So R can match with 1. Reaction with ninhydrine gives purple color, so which indicates the presence of amine group. And it also reacts with FeCl3 to give violet color. So the compound is having a phenolic unit also. FeCl3 test is a characteristic of phenolic unit. So both primary amino group and phenol units both are present in the corresponding compound. So that could be compound P, because it has an H2 group, it has phenolic unit as well. Reaction with glucose will give corresponding hydrazone, that is with hydrazine. Okay. Now Lassane's extract of the compound treated with dilute HCl followed by addition of aqueous FeCl3 gives blood red color. Blood red color can be given if the compound is having nitrogen and sulfur along with carbon, and none of these compounds is having sulfur content, right? So we are not expecting any matches for fourth entry. And last one, after complete hydrolysis it will give ninhydrine test. Okay, that means amino acids are generated on hydrolysis, because these two are peptides. Okay, you can see this is a dipeptide, this is a dipeptide, and you know which are the amino acids involved in the dipeptide. Okay, you know the structure of amino acids also. Here complete hydrolysis will give ninhydrine test. It's okay. We are getting amino acids from hydrolysis. After that, it does not give positive phthalate dye test. That means it is not generating any phenolic units. Okay, no phenol content. So it has to be the peptide Q. Okay. So the correct matching has to be 2, 5, 1, 3. 2, 5, 1, 3, which is option B. Okay, so that completes paper 1. Thank you.